I am Liberato Ferrara. I am professor of structural analysis and design at Politecnico di Milano. You can see this is our main building where the rector office is in springtime with this nice park, nice garden around. What I'm going to talk to you about is the use of high performance concrete, high performance fiber reinforced and adhesive composites. You find in the literature a lot of different acronyms to define basically the same category of material as an ideal material candidate for the retrofitting of existing structures. And let's start from the big picture. Construction industry, well, these are numbers related to pre-COVID, but they are still significant. Construction industry takes into account works for 6% of the world gross domestic products. And in the world, 100 million people are directly employed in construction industry. The construction industry is very widespread in technologies, performances, and so on. You can see here a variety from traditional to very colorful. Our Indian friends may recognize this is a lady in Jaipur in India who was doing some construction work. But which are the challenges we have to think? Which are the cutting edge frontiers of the construction industry? Transportation infrastructures. We have realized that when we were closed at home, how important was the supply of the goods, of the freights, and transportation plays this role. Most of all, you have to consider that 1% investment in gross domestic products in infrastructures result in 4 years, so in a very, very short time, into 1.5% increase into the GDP. And also, our infrastructures worldwide are aging. This is quite natural. We built them 50, 60 years ago. Now they are aging. They are also aging because the volume of traffic, for example, has continuously increased. So we are demanding more and more to our structures. And every year, the delays in traffic, the interruptions, cost every household, every family, $3,600, just in money that goes out, and you don't know why. Coastal protection. We always hear about climate change, which is nowadays a reality. And we have more and more frequent extreme weather events, which actually stress our structures. This picture was taken 2 years ago in Malta, in springtime, where everybody would like to go there to get some sunshine, and you end up with this, and you cannot fly in and cannot fly out. This is breakwater in the harbor, was built during the Second World War. It's quite an interesting historic structure to look for, and they have problems of cracking off. This is typically a large-scale structure fracture mechanics problem. Some of you have familiarity with. Also, we have to take into account that we have to look for coastal defense structures, because just in European Union, 700,000 people live in areas which are exposed to coastal flood. And we have a huge coastline, 6,000 kilometers. US has just 1/3 of it. Green economy, decarbonization, what does it mean? Well, first of all, it means that we have to reduce our dependency on fossil fuels. This is another big problem because we cannot simply go to the mine shaft, close it and forget it. It's a big problem. But if we have to promote the use of renewable energy sources, this is a geothermal power plant, we must make this energy harvesting, this energy source more competitive, to say. And it's not just a matter of drilling the hole and harvesting the energy. There are structures and infrastructure in service of that. You can imagine that the water that you extract from the soils has a huge quantity and different types of aggressives into it, and they attack the structure. So this is a problem that we have to say, and that civil engineers working with construction materials, we have to provide a solution to this. We have to provide a solution to make offshore wind energy more competitive. And this is also a huge field in which we can. And there are also a lot of sectors which are related to what is called blue growth. Think of it. How do we call our planet? How is it called? Earth. What is made of? 70% of it is made of water. So it's just like an oddity. But the fact is that only 5% of our economy comes from the sea. For example, 5% of our food and 95% comes from the earth. So there is a disproportion. So we have to invest more and more into sectors which can promote a sustainable, respectful use of the sea resources. And some of them may also be interesting for us. So which is the scenario? Some of you may recognize this picture. This is the Museo do Amanhã. Did I say it correctly? It's Museum of Tomorrow in Rio de Janeiro. There is a very interesting exhibit inside which stresses upon humankind has become a geological force in the sense that we shape the planet. So we have this responsibility. We have to shape it in the right way, not to destroy it. And as engineers working with concrete, we have the responsibility of using in the appropriate way a material which is the second largest material used in the world. First one is water. So it's the first man-made material that we use. Every year, more or less, we produce 10 billion tons of concrete. So it means that each one of us has like a dowry of 1.5 tons of concrete per year. And we make structures, we make infrastructures, we make iconic buildings like this one. This is the oldest concrete building still surviving in the world. It's the Pantheon in Rome, which was made with a functionally graded concrete. We think that this concept is relatively new, but the Romans adopted it because they made concrete with travertine aggregates, very strong, very hard in the basement, and they started reducing the strength of the aggregates as long as they go up. The dome is built with pumice aggregates. Pumice is a stone which floats, just to reduce the weight. And you can see how the thickness of the dome also reduces. So there was some ingenious structural design into that. The other thing is that, look here, the dome starts here, whereas the wall goes up to here. If you are familiar with shell structural analysis, this is the point where the parallel forces move from positive tensile into negative compressive. So where the tensile, the hook forces are tensile and concrete cannot resist them, the Romans put the confining wall. And where the hook forces were compressive, which concrete can resist, they left the dome free. This is a concept that, for example, Brunelleschi and Michelangelo had completely lost when they built their domes, which actually suffered cracking exactly in this area here. So this is just to tell you that as engineers, we have to merge material and structural concepts. I like to say that we must learn to think holistically. This is our responsibility. And we also have to think beyond the meter cube concept. We speak about cost per cubic meter, ton of CO2 per cubic meter, everything per cubic meter. This is a nice unit. We cannot get rid of it, but we make structures. And for example, if you look at the energy which is required to produce 1 ton of material, look where concrete is. So I will say it's quite sustainable. So, well, cement is a little bit higher, but cement is just an ingredient of concrete. So why concrete has such a bad publicity, say, oh, it's not environmentally friendly. And I'm quoting our colleague and friend Karen Scrivener from EPFL Lausanne, and she said, simply because we use a large quantity of concrete. If we have to think of making the same things we build with concrete with any other material, the carbon footprint would be much more disruptive than what we have. So we have to take this in mind. And take also in mind that cement is a commodity nowadays. These are pictures, well, this is India, Niranjana and Priya can confirm. This is Tanzania. You can see it, you can find it really on the streets, like in an open air market. It's a commodity. But cement and concrete suffers from a problem. Like stones, they do not have a good tensile strength. So we need reinforcement into that. And why? For several reasons, the marriage between concrete and steel is an excellent marriage. We have to consider that steel is the weak part of it, because steel, when it's exposed to environment, is subjected to corrosion. Concrete protects it, but concrete cracks. And so immediately a highway is open for the aggressive environments to go on. And each year, the cost of repairing corrosion damages, they sum up to 3.4% of the world gross domestic product. So you can imagine that we work for part of our work just to repair these damages. Concrete cracks, we have said. And if you pick up any structural design code throughout the world, wherever you go, you find sentences like this. Cracking is normal in reinforced concrete structures. Concrete cracks, you cannot avoid it. And when I teach the beaming bending to my students, one of the first concepts that I try to deliver is that we want concrete to crack. Because if concrete does not crack, steel works at 20, 30 megapascal, which is less than 10% of its yielding capacity. So what is the matter of putting there a material which works at 10% of its capacity? It's not wise from the engineering point of view. But you also find a sentence like this in the code: cracking shall be limited to an extent which will not impair the proper functioning of the structure and the durability, causing its appearance to be unacceptable. This brings me to another concept. When we design generally a concrete structure, our approach is this: we design for ultimate limit state and we check the serviceability. This is perfect, this is okay. Well, if you go for ultra high performance structures, more likely it's not so obvious that once you have designed it for ultimate limit state, serviceability is okay. But just remember that ultimate limit state is something that we design such that it never happens. Serviceability is something that the structure will experience throughout its life. So we have, in a sense, also from the educational perspective, to bring back importance to what is the service scenario of the structure, because that is what the structure will experience throughout its life. And one of the main parameters that we are called to determine is the crack width. We have in codes very reliable models for ordinary reinforced concrete structures. They are based on a simple tie. You apply a force to the bar, and once this force reaches the strength of the concrete at a certain cross-section, you form a crack. When you form a crack, the stress in the concrete drops to zero. Is not exactly true, because also plain concrete has some residual toughness, but we consider that it goes immediately. And the same stress is taken by the steel. Then you need some length, a transfer length or bond length, through which the stresses go from the steel to the concrete, are redistributed, so to restore the coupling action between the two materials. And by simple equilibrium consideration, if you go back to any of your structural mechanics, structural design handbooks, you can find this equation. You find here that this transfer length is related to the bar diameter. Okay, keep in mind this concept. Then if you write some other equilibrium and you consider not only the bar, but the wall segment, here is a crack. And here you have the couplet action, concrete plus steel. You find what is the increment of stress, the stress transfer, which must go from steel to concrete and vice versa. So you combine these equations and we find that, the transfer length is proportional to the bar diameter and is inversely proportional to the amount of reinforcement. So the issue is that with reinforcement, you do not avoid cracking. You need pre-stressing to avoid cracking. It's not that you put more reinforcement, you avoid cracking. No, that is a very bad idea to propose. But given a certain amount of reinforcement that you must put there for other requirements, there is this parameter that you have to take into account, which is the diameter of the bar. The smaller the bar, which means also the higher number of bars that you have to put into there to get the same power, the smaller is this transfer length. This transfer length, anyway, this transfer length also is related to the crack width. So we calculate total crack width as the unit crack width, the difference in strain between steel and concrete. You can work out these equations from any handbook, and you multiply by this length parameter. So this means that if you have smaller bar diameters, you will have more cracks, but each one of them will be smaller. And this is good from the structural point of view, because the crack width is the parameter which governs the durability, but it also governs the loss of stiffness, which impairs the serviceability, for example, the deflection of the structure. So this is what we generally do for cracks, which are caused by mechanical actions, can be forces, can be restrained deformations that induce stress. But there are a number of phenomena that can cause concrete to crack that we do not know how to handle, how to calculate the width of crack due to this. And most of these phenomena, they do really occur in very early ages of concrete. For example, plastic shrinkage is due to some differential evaporation. You have a gradient of water. And just some examples of an experiment we did with a homemade setup that we built. It costed us 50 euros going to buy the pieces in the stores. So this was the specimen, this was a heater, this was a fan, and we had here a pot with water on a scale just to check the water evaporation rate, which is the parameter set by the standard. You see, this was the setup once opened that, some pictures, and you see the cracks. This is the crack width monitored with a manual or portable microphone. The cracks started appearing 1 hour and a half, 2 hours after casting. So you just cast and the crack starts. And well, the setup is made to exacerbate crack, but we had cracks up to 1 millimeter. And this is, for example, one of the cases in which any self-filling technology may help, because these cracks immediately appear. You can hardly do with them well. You can check the curing status and so on. But if you have something which helps in closing them, we use it in this case, pre-soaked lightweight aggregates, which helped in some kind of self-curing, I would say, supplying water. We were able to cope with that. And similar things you may do with restrained drying shrinkage, which also occurs probably even before you put the structure under loads. And this is the ring test. You can see here some images. In this case, the cracks appeared 7 days after casting, which is not so early, but still it's before you complete and you put into service our structure. And you also have models to predict the appearance of the crack, because you can build up your strength development curve and you calculate with linear elasticity formula the stresses in the ring from the strain gauges that you put, and you when the curve has to meet, you find the cracking moment. So what is the idea behind the ultra-high performance concrete process? We have seen that concrete cracks and the crack width is proportional to the bar diameter. But if you think of a bar, the smallest commercial diameter cannot go below a certain threshold, because also it still has to comply with some ductility requirements and so on. If you look for ductile steel, the smallest available diameter you find on the market is 8 millimeters, more or less. So what shall we do if we want lower and lower reinforcement bar diameter? Just go into fibers. Fibers can have millimeter bar diameter, millimeter wire diameter. They do not, except for special mixes and special cases, they do not increase the tensile strength of concrete. It's not that. But they increase the capacity of the concrete to resist crack propagation. So they control the opening of the crack. And all of us working with self-filling technology, this is important for durability, but all of us working with self-filling, we also know that a crack which is narrower, has a narrow volume, is more easy to be filled, to be repaired. We have now in the codes, we are now in the standards, the tools to identify the properties of fiber reinforced concrete. This is a 3-point bending test on a notched prism. You plot the results, you make the test, you record the results, you plot the results in terms of nominal stress. Just keep in mind, this is not a true stress. First of all, because the test is a bending test and is not a tensile test. But also because we calculated the stress from the load. We never measure a stress, we measure a load. And from the load, we calculate the stress using the Desaint-Venant solid formula. Desaint-Venant assumption is linear, elastic, homogeneous, isotropic. Concrete is not even that. So this is just a way in which we convert the load into stresses, so it's nominal. And we identify the stresses at different levels of crack opening. In fiber reinforced concrete, we pick up 0.5 millimeter and 2.5 millimeter as relevant crack openings. And if you work out these numbers, you can realize that given the geometry of the specimen, 0.5 millimeters corresponds to a strain, to an average strain on the cross-section, which is equal to 2 per mil. 2 per mil is more or less strain at which the conventional reinforcement yields. If you have 400, 500 MPa steel, divide by Young modulus, you have about a yielding strain of 2 per mil. And 2.5 millimeter corresponds to an average strain of 1% of the cross-section, which we can set as a conventional limit for tensile strains in a reinforced concrete cross-section. So the code is made in such a way that fiber reinforced concrete is homogenized, is made compliant with ordinary reinforced concrete, because one of the issues could be that you can use both of them, fibers and conventional reinforcement. So you need a method to match them together and make a consistent design. So if we pick up the spacing of the crack as a parameter, where is the effect of the fibers? Well, in the codes, you find that the effect of the fibers is here. This is the tensile strength of concrete. This is the residual post-cracking strength that the fiber reinforced concrete can guarantee you. So the fact that concrete can take some stresses even after cracking reduces the crack spacing, and then is beneficial further to the crack width. So if you iterate this process up to crack spacing saturation, you do not have any more space to form a crack. Here is the concept of ultra high performance concrete. You form the first crack at this point here. If you would have ordinary concrete after this point, your stress would immediately soften. You have high performance concrete, you have fibers inside. So what do the fibers do? They pick up the stress from a crack and redistribute to the neighboring cross sections, and you can form another crack, and you can form another crack. And as long as you can form cracks up to crack spacing saturation, you follow this strain hardening, which can be more or less steep depending on your mix design and so on. And you have this multiple cracking and strain hardening capacity. Well, obviously, this depends on binder content, water binder ratio, use of superplasticizer, you use very small maximum aggregate size, fiber dosage, fiber orientation, several parameters. But this is the basic concept. So how do we identify? These are results which are taken from one of the research projects in which I was involved as coordinator. Some of you also worked on part of it, which is the resilience project. Well, these ultra high performance materials, well, if you come up with the cost per cubic meter, you jump on your chair because it's 4 or 5 times as much that of an ordinary concrete. But they are thought to be used in very thin elements. So we cast very thin beams. We performed 4-point bending test in this case because we wanted here a zone in which we could have multiple distributed cracking. And then we also developed a test methodology, an indirect tensile test methodology, which is this one. We call it the double edge wedge splitting. You have these square tiles, we cut grooves and notches, and then we apply through some devices a compression force. So the principle is the same of the Brazilian splitting test. What do these grooves do? Well, they deviate the compression forces far from the ligament, so that we checked it with finite element analysis. We have on the ligament a pure tensile stress state. And you see, these are experimental results from this test. The purple curve is the one that through back analysis, through back identification based on force and moment equilibrium equation, we identified from the bending. So there is some consistency between the results. And this is the simulation. It's interesting to see that, for example, these were tests made on 100 millimeter deep beams, and our prediction was on the upper bound. These were tests made on 30 millimeter thin beams, and our prediction is in the lower bound, because in 30 millimeter thin beams with 20 millimeter fibers, all the fibers are aligned in the right direction. So you have an improvement of the performance. In 100 millimeter beams, the orientation, the alignment of the fibers is more random. This was just to recall once more the idea of the cost per cubic meter. Well, probably this 400 euros per meter cube now is even a low estimate because of the change in prices. But see, 50% of the cost comes from the binders. This is a typical mix design. And 35% of it comes from the fibers. The rest is a mixture, which is quite important. You see, it's 3% of the binder content. It's a huge quantity of a mixture. If you go to a normal concrete, you have 1% of cement as an average. But this is just to comply with the requirements of the mix design. So what you have to ask is, what can I build with 1 cubic meter of material? And think in a life cycle perspective, and what we have discussed also throughout these days is, surely I can have a higher initial cost of my structure, but my structure will be more durable. So I have to intervene with the first maintenance, not in few years, but later in time. And this will bring me to a recovery of the cost. So other concepts, other information, other actors come into play in order to evaluate this. Another thing, when we use these materials for retrofitting, we have to think of the durability of the retrofitting. And this is a survey which about 10 years ago, the European Commission promoted, and 50% of repaired concrete structures were shown to fail once again, and 25% of them 5 years after the first repair. So you can imagine that from an investment point of view, this is continuous drainage of money, because every 5 years you are forced to put back that money, resources, materials, and so on into that. The first project I was involved in with using these materials for retrofitting was dealing with earthquake engineering. Shear walls, and most of all, well, we have shear walls in buildings because they are the system to which we resist lateral loadings, but we must have also openings in shear walls. Hardly they can be monolithic, because we must have windows or doors and so on. So the important thing is that how do we design these coupling beams which pass through the opening and connect one shaft to the other? Because we rely on shear walls for their stiffness. But you can imagine that if the stiffness is that of the solid wall, okay, it goes with the cube of this dimension. But if you have to rely upon separate walls, the stiffness will go with the cube of something which is less than half. So the stiffness will be 1/10 more or less of it. And this will dramatically decrease the stiffening capacity of the shear wall. We can design the coupling beams so to restore, here is the concept, you can rely upon the lever arm of the wall, or you have to take them separate. But if you want this coupling beam to restore the coupling between two shafts, you see the reinforcement detailing that you must perform. You must put this crosswise reinforcement, and you see that in order to anchor them, you have to go halfway up and halfway down. So this is surely, okay, you can do that for new constructions, you design them in such a way. But pick up any building built everywhere in the world between the 50s and the 70s. Why do I say this? Not because they built badly, absolutely not. But because at that time, in most countries, even strongly seismic countries, there were not any seismic code enforcing. Only few areas were, labeled as earthquake regions, because that was based on historical records. And historical records were mostly the baptism registry of the churches. And so they realized that what was happening. So this is quite interesting. Those in the picture in Alaska where a project was made. So you see, using these materials, you go from this kind of detailing, which is very demanding, to a less complicated detail. You use less reinforcement and you get the same capacity, or even better, because here we are at about 450 kilonewton, and you go here higher, and the cyclic capacity as well is okay. Well, if you have to upgrade a structure to retrofit it, you have different technologies. So we wanted to use this high performance material. This was the detail of the setup. You see, these are our specimens. The coupling beam is this part here. And this was a coupling beam which replicated a structure in which no seismic design consideration was taken into account. It was just minimum reinforcement for non-earthquake regions. And these other parts are simulating the shear wall, so they were over-designed, over-reinforcement. This was our setup. You have to imagine the specimen was tilted up at 90 degrees in order to make the tests, and this was how it was functioning, because we wanted to apply cyclic loadings. And we tested, this was a beam without any reinforcement, shear diagonal crack. Theory is perfectly respected. Then we put longitudinal reinforcement with a strut and tie mechanism. And then we put our material, and this was the envelope, the monotonic curve, and these were the cyclic tests that were performed. This was the failure mode. You see, this was a typical failure mode of a compression strut, which fails. So we went into retrofitting. The material was more or less same. We used less fibers than what we would use in a new structure, because the requirements were different. It's not exactly mandatory that you use huge quantity of fibers. Use them for the requirements that you need. The material was very fluid. This was a master student working at that time on this project, and these are the results. So we pre-damaged the structures, then we applied the repair, and you see, compared to, we had 60 MPa, we went up to 200 MPa with the repairing. And you can see this crack here, which was formed in the subgrade. You see, it resulted into several multiple cracks on the retrofitting. So we were able to spread this localized damage into several multiple cracks. And this was the advantage of using this material for enhanced structural capacity. And compare the control specimen non-retrofitted with the retrofitted ones with different technologies and different amounts of pre-damage. So then we went into modeling. I will not spend too much details into that because it was conventional finite element model. We simulated the test. We got good agreement for the monotonic, for the cyclic tests. What we wanted to see, now we have to scale up. We started from the material. We went to a mesostructure, I would say. Now we scaled up to the structure. This is the process that any engineer has to do when designing. And we said, okay, imagine that we have a medium-rise building. Is it necessary that we retrofit all the coupling beams at all the stories? Or we can just intervene where it's mostly required? So we use a conventional structural analysis software. This curve here is when the two wall shafts are completely separate. And the one with the black dots is the wall without any opening, so completely solid monolithic wall. Then we said, okay, what if I have a coupling beam which is designed not for earthquake requirements? You have the hollow dots, the hollow squares here. What if I retrofit all the coupling beams? I have the diamonds. Okay, there is an improvement of the capacity. Obviously, you do not get back to full solid wall, but you have a remarkable increase. And then we said, well, what is the most stressed beam here? Are the ones at the bottom stories. So what we retrofit only the coupling beam at the first story. You see, barely you can notice any difference if you retrofit all of them. So this was also to mean that, okay, the material is okay, the behavior at the mesoscale level is okay, then perform a structural design, because this is also a matter of economy of your design. So just retrofit, well, if you have to go to higher rise, you probably have to retrofit 1/5 or something like that. But this is something that you can do, is design the retrofitting from the wall scale, from material to structure. And here is an efficiency parameters that we checked just to provide some indications to the designers. Now the thing comes, okay, if you have to what we did, when you go to build up a finite element structural model, you are quite sure of what you have done. You don't use a finite element model to design, you use for check, because this requires time. So you will never do it again and again and again. So you need some tools to make the design calculations on the back of an envelope. Also because in that case, you have your own numbers to check with that of a computer. So the methodology is very simple. This is something more or less everybody of you is familiar with. The design of a reinforced concrete cross-section. You have a compressive stress block for compressed concrete, and you have the tensile force in the steel. Very simple. If you add a layer of ultra high performance concrete material, you simply add a stress block on the tension side for this material. And the equations are exactly the same. You write the force equilibrium equation through which you calculate the position of the neutral axis, and then you write the moment equilibrium equation through which you calculate the capacity of your beam. These are the equations. Force equilibrium, compressed concrete, steel, tensile UHPC, you find the neutral axis position, and then you go for moment equilibrium about the centroid of the compressed stress block. You have the contribution of ordinary steel, and you have the contribution of UHPC. That's very simple. Then you can specialize this to different cases. What if the steel is not yielded? You know, this is conventional reinforced concrete design here. But just have in mind that this is very simple. You have another term. Concrete can take tensile stresses. This is the conceptual difference. Then you have the model, equilibrium follows. As the Latin says, res tene verba sequentur. Hold the things. The words will come later. So all the physical concepts, if you have them, we are engineers, we can write down through mechanics a force and a moment equilibrium equation, and they will follow. One important thing is this. this is a paper which was published about 10 years ago, in which they used this material for jacketing. So it was meant for shear and bending retrofit. And then they made some, calculations, some design, and they realized that, okay, well, if we predict our ordinary reinforced concrete, our models are very good. But if we predict our model with retrofitting, what does it happen? The prediction is much better than the experiments. So this means that our model is not on the safe side. Well, because what did it happen? The material parameters were identified to a direct tensile test. You see here, there was quite a remarkable strain capacity deformation, up to 0.5%. But what happened in the reality? In the reality, the non-retrofitted beam, you see, had this very, very distributed cracking pattern. When they went into the retrofitting, they were just one single crack. In this case, the bond was so good that the crack formed, but the redistribution length was so narrow that they were not able to redistribute and take the advantage of all the deformation capacity of the material. So they played with the parameters and they realized that this was the problem. So in that case, it's also a balance of guaranteeing a good bond, but the bond must be such that you are able to redistribute the crack, the damage from the subgrade to the retrofitting stiffness. Then I put here as an exercise for you the case in which we are going to retrofit a column. This is an interesting application because, first of all, because it can be done with very limited invasiveness. You really make a narrow hole on the slab or top floor and you pour the material from the top, or if you have an adequate pumping equipment, is a little bit more difficult because with a lot of fibers, your pumping hose may be damaged by the steel of the fibers. But it has been done, for example, in a number of public buildings and schools with very limited invasiveness. You have just 2-3 centimeters thickness, which also means that if you go in earthquake retrofitting, you do not alter the stiffness of the building and you do not decrease the space. If you have to go for conventional concrete jacketing, the minimum is 5-6 centimeters that you add on both sides. So you lose 10-12 centimeters on the 4 sides, you lose space around, and your stiffness may be altered. And when it comes with stiffness for earthquake design, it's very, very problematic. So for a column, you can have different ultimate limit state conditions. The cross-section is purely under tension. You have the strain in the tensile UHPC going at its limit. You have the strain in the compressed concrete going at its limit, or you have the purely compressed cross-section. And for each one of these cases, you have a different distribution of strains, distribution of stresses over the cross-section, for which you write force and moment equilibrium. So you can build up, if you go back to your design of reinforced concrete, you build up the moment axial force failure envelope. You use it just to make your final design. I reported here, for the sake of completeness, all the cases that you may have, and you will have in your in the slides, which will be surely made available. Well, the equations may look complicated, but after you have written them, you write your own worksheet, and it's good that you write by yourself because you know what worksheet will do. You will not use it blind, and you can use it for your purpose. If you want to do some homework here, there is also a homework assignment for you to practice this. So just going a little bit into the project I was talking before. In this project, we developed this we call it them ultra durability concrete materials. It's just the concept of material. It's not a specific design. What we wanted to show is that you can make these ultra high performance, ultra durability materials with locally available constituents tailored to the intended requirements that you need. 14 partners throughout Europe, crossing the whole value chain of the concrete construction industry. Some of them are also partner of SmartThings as well. And we have built and we are currently monitoring 6 structures in Europe. 2 of them are in Spain. Some of you have already seen the mussel raft or the offshore wind floater in Sagunto port. 2 of them are in Italy, are in a geothermal power plant. Surely David and Niranjan came to to visit it. One is in Ireland, is a pontoon in a harbor. And dealing with retrofitting, we did an interesting case study in Malta, in the Valletta harbor. It was a water tower built by British between the two wars. So it was something like in the early 30s. So it's about 80 years old. And the concrete was excellent because we took the course. The project was led by my colleague, Professor Ruben Borger, and I'm going to show here some of the slides that he has given me for this purpose, and he has agreed to be shown are his slides. So you see here the tower was severely damaged by exposure to airborne salts, airborne chlorides. We thought this was in beginning, when I look at the picture, I say, okay, this is the phase exposure to the sea where the winds come from. Actually, it was the opposite side. So it was a combined effect of the wind suction. You know, when wind comes, you have pressure and suction on the other side. So this was the part where the suction, main direction of the wind, the suction where there was erosion and effect of the chloride. So it was a combined effect. But we took course on the other side, which was perfectly intact. And after 80 years, the concrete was 40 megapascal strength. Real strength of the structure, of the concrete in the structure. So obviously, when you go for retrofitting, you have to make a survey. You see, this was the status of the inner part of the tower. So the grass was growing because it was completely abandoned. So we made a survey also with drones. These are some pictures. These slides are by Ruben. This is where the area, these are the Maltese Islands. This is Valletta, and the harbor area is here where the tower is. Here is the breakwater that we saw in the previous picture. This is the strategy that you have to follow. You have acquired documentation, you have to make an assessment, a modeling, you have to select the material, go to the construction process, and actually in the resilience project, we implemented also a monitoring system and created a technology and e-learning platform, which will stay after the completion of the project, so the results will be made available. So you go for historical documents, very nice blueprints that you cover. We went for drones, constructed 3D image models. Survey was made to identify the position of the reinforcement with conventional tools, and the reconstruction also through 3D images, some thermal imaging to see where the damage was, to identify delamination and spalled concrete. Then a structural monitoring, a structural assessment was made, identifying the natural frequencies. So you see, it's quite a flexible structure because the frequency is about 3 Hz. 3 Hz is, just to tell one thing, is the frequency for which now the wind towers are designed, because the blades, in 1 second, the 3 blades make one complete turn. So this is 3 Hz. So just to give numbers to which we may become familiar with in our design processes. And we started in 2019 to think of it, and we arrived at, after 2 years, to have the structure back into full serviceability. Obviously, a different kind of expertise were made because there were some lichens, some shells which were found into them. So there was some biological life into the basin of the structure. Then the material was selected and tested, was ultra-high performance, ultra-high durability concrete with 1.50, I think, steel fibers per cubic meter. Mixed design details are usually available, and the durability performance was characterized with accelerated chloride penetration tests. The important thing is that we had to retrofit the columns of the tower. So first of all, in Malta, they built a replica, small columns that they, jacketed with this material to check the different requirements on the bond between the subgrade, the stiffness of the material. These are tests similar to ones that Daniel has shown. So they are tearing off tests just to check the bond level. Then to retrofit the drum, a different technologies was used because it was too difficult to build a scaffolding in which the fluid material could be poured. So we used a textile reinforced concrete, which was highly thixotropic, so we could apply without formwork by hand, and there was a carbon textile reinforcement for corrosion resistant requirements. Then once the material were selected, the retrofitting was designed with a structural analysis. You have to identify the stresses that you expect and that material has to withstand. So we went up to this. So the lab work then started the site work, removal of the all the parts, preparing the surface. In the case of reinforcement, there was replacement of the damaged one, but was also realkalinization of the surrounding concrete. It was damaged by carbonation and chloride corrosion, patch repair, build the temporary supporting structure, and go up to the completion of the work. So you see, these are the replica structures of the curved wall and of the columns, which were built and tested in the lab, different tests which were done. These were some images, removal of the cover. The tower was already retrofitted in the 70s, so there was already a 7 centimeters jacketing above, which had to be removed. Was the removal of the past intervention and the treatment of the existing material. You see application of corrosion inhibitor and mortar repair, and this was done, patch repair of elements which were needed, different images of the site, and epoxy injection and sealing of cracks, different operations. One important thing, you can see this picture. What is strange about the light here? All this work went done during night because the construction work went on during summer in Malta, and in the daylight you have 40, 45 degrees, so it's really hard to work with this material at such a I have some other pictures of here it is. Actually, the work was done in the night shift. So this is something that you have to take into account when you plan your construction site, if you have to comply with some time requirements and so on, because only in the night temperature dropped below 30 degrees. And these are some images of the tower as completed, you can see here. And a lot of sensors were installed for, you know, corrosion monitoring, strength, temperature, accelerometer, crack monitoring, and also weather station with all the tools to monitor the weather condition. These are some images of the sensors. Obviously, also cabling that they counted that there are 15 kilometers of cables all around the tower just to monitor it. Some, you know, boxes to protect them and to hold them and bring them to the station. And there is just a hut, a cabin there where all this. So these are some pictures of the project completed. Really, it has a new phase, and this was the first test that they did. This is Professor Borg, the colleague responsible from that in Malta. Ruben, you know, we know them from Sarkos cross-section, and actually this is the picture with this very nice blue water that you can see here, up to complete filling, and is there. So just compare what it was before, what it was just a couple of years ago, and what is now this structure. And some of us also went inside the tower, which was quite nice. So if you want information on this project, Ruben will be able to and happy to report. So just trying to wrap up, we have these fantastic materials, I would say, to build new structures and retrofit them. And what we have to do as engineers, as structural designers? Well, first of all, we have to design for now, for the time of construction. And with this material, surely we get a higher performance than if we design with ordinary concrete. This means that we can also optimize our structures and use less material to get the same performance. But then the benefit of this material comes from the fact that they have a higher durability. What does it mean? That the degradation of their performance is lower in time. Is much, much slower. So instead of having, this is the diagram we have seen in these days quite some time, is the Tutti diagram modified. You have some initiation period, and after you arrive at that, it's the propagation period, which rapidly brings you to the decay of the performance. And at a certain point, your strength, your performance capability will no longer meet the demand. And this is where your structure will fail. But your useful service life will terminate before, because you will never end up, this means safety factor 0 or safety factor 1, basically, depending on how you define. You will never end up with this. You want to stop earlier and go for a major retrofitting. Either sometimes you want to stop here in the early stages, because after that you may lose it rapidly and it will be too late. So with this material, we will have a slower degradation of the performance. And if we embed the self-healing functionalities, we can even have as lowering down, because as soon as the damage occurs, we have the capability, faster or slower, more or less effective, to go back to the initial level of functionality. This requires all of us to start thinking in terms of a life cycle perspective, not to limit ourselves to this very first moment. And just a few ideas, just to go beyond the technical. If you go on the website and Google for this paper, The Role of Materials in the Post-COVID Society, this was a reflection paper published 1 year ago by European Commission, Alliance, European Material Modeling Council, Alliance for Material. There are different associations working in fields we are involved in. There was this sentence, which was quite inspiring. Materials can help to create a less dependent, more resilient European economy by guaranteeing raw material supplies. One of the purposes is that we can make these materials, we must be able to make these materials with locally available products, not just a branded product, a luxury product that you buy in a nice, you make them combining different functionalities that you have, ensuring higher materials durability, higher energy efficiency, higher degrees of materials recycling. So let's start thinking whenever we design that our structure and our material can be decommissioned, can be reused, and our material saving to optimize a product by design which announced repair. Then going from technical to literature, these are the very last slides. This is a book by an Italian writer, which I loved it. I encourage you to read because it's very inspiring. 6 Memos for the Next Millennium was published in 1985. Italo Calvino was supposed to deliver these lectures at Harvard a few months later, and he died before going to the US. They are really 6, lectures, and he highlighted 6 keywords, we will say, for the society of the 21st century: lightness, quickness, exactitude, visibility, multiplicity, and consistency. Obviously, he was a writer, he spoke about literature, he spoke about society. But let's try to make this exercise in these last minutes. What do these keywords mean for us as civil engineers? Lightness could mean that we use less material to guarantee the same performance. So we reduce the burden on the environment, because every time we need to quarry the material, we are subtracting something. Quickness, well, obviously, we want to construct faster, but also, for example, to make our retrofitting interventions faster because they are less invasive and they cost less also in terms of, the outcome on the people who are using the building and so on. Exactitude, just design the material for the level of performance that you want. Visibility, with these materials and with new developments that you have nowadays, there is a lot of speaking about 3D printing with concrete. We really could merge shape and structural functions. Multiplicity, we showed the example of the pantry. Functionally graded materials, functionally graded structural elements. And then consistency. You cannot use all these advantages if you do not have a design approach which is based on the whole life cycle of the structure. Okay, well, you know me, but for people who follow online these are my contacts. These are the social media in which with the different projects we have talked about, we are present. And this is my research group in pre and post-COVID configuration. This is a suitably spaced matrix of people in our garden. And thank you very much for your attention.
We don't have any questions.
Okay.
But I have a question.
Yes, please.
Yeah, thank you so much for your nice presentations. But I was wondering whether the inclusions of the steel fibers in UHPC increase or reduce the corrosion performance of the concrete, because we all know, that.
Well, that is a quite challenging topic, and I am quite well prepared because I was just reviewing an ACI document last night, so I studied it very well. Actually, the corrosion of steel fibers in fiber reinforced concrete or also in hybrid fiber reinforced concrete, the fiber itself really corrodes if it's exposed to the surface. And it has been demonstrated that you really need less than 1 millimeter mortar wrapping the fiber to protect it from corrosion. Well, this applies if it appears on the surface, but it's just a spot of rust, but also if you have a crack, an open crack, and obviously the fibers corroding the crack. But the corrosion has been shown not to proceed farther than a few hundred microns on both sides of the crack. The other advantage is that the fibers generally do not create a continuous network. So you corrode few fibers, but then it stops there. Whereas in a bar, the corrosion starts, but you have continuous supply of the electrons for. The other thing that has been shown is that since the fibers help in keeping the crack width narrower, they delay the penetration of the aggressive agent. So they have a beneficial effect also on the corrosion of the ordinary reinforcement. But anyway, this document is going through the approval process in ACI. As soon as it will be published and available, I will be happy to share with you because it really contains a lot of valuable information. It's a document prepared by the technical committee of ACI on fiber reinforced concrete, which I'm chairing. So we are in the final process of approval. Anyway.
Sorry, for in continuance of my previous questions, because as you say, for example, it's about the surface of the concrete, and for normal corrosion tests, for example, static migration tests or RCPT, we are creating a concrete piece from the sample. So the SC fibers is at the end of the sample. So can we use those kind of experiments?
Well, that is a question, because in that case we are really forcing. You can still get some results which are useful, for example, for comparative purposes. They are quite useful. A thing that we noticed is that if you have a lot of fibers, then, for example, detecting the penetration with the silver nitrate can be really cumbersome, because really the change of the color is not so clear as it would be in an ordinary concrete. And for this reason, I don't remember whether Vanessa presented something, and in the Sarcos cost action, we did an interlaboratory testing. We went for multi-position and multiple depth titration just to check the effective resistance to chloride penetration, and we did also for long-term exposure up to 1 year. Also because with COVID specimen, we are forced to stay in chloride solution for longer times because labs were closed. So this was one of the benefits. But we really realized that in that case, you have very, very low values of apparent chloride diffusion coefficients for this material in the range, the numbers that we had heard about, a few 10 to minus 13 square meter per second. Yeah.
So for presentation, I just have a simple question of the fiber selection. As you mentioned that the smaller the diameter, then we require less of the amount and have smaller fibers.
Yeah.
So as compared to steel fiber, is there a trend to use the polymeric fiber, as we know is even smaller?
Yeah, sure. You must use structural polymeric fiber, because polymeric fibers have a broad range of varieties, much broader, much larger than steel ones. But surely there are also polymer fibers that can provide same, mechanical performance as the steel one. There is a big, debate, steel or polymer fibers. If you look at mechanical performances, it's okay from the durability point of view. You can also say that polymer do not corrode over time. The issue with polymer fibers is their sensitiveness to higher temperatures, because after a certain temperature, the polymer fibers, some of them are no longer there, basically. So if you have a structure which is also sensitive to fire, you have to consider this requirement. The other thing, which is a completely open topic, I know a lot of work has been done in Valencia by a group of Pedro Serna, is the creep of fiber reinforced concrete under flexural or tensile loading. And in the case of polymer fiber, you must consider also the creep of the fiber itself, which can be obviously different from the creep of the steel fiber, which you can neglect. But surely, if you limit ourselves to mechanical performance, and we eliminate the cases in which fire can be a problem, you can make UHPC, for example, PVA fibers. A lot of experience both in lab and application exists about this type of fibers.
We have
Yes.
a question from the chat regarding what is the design like of HPC with the fibers?
What is the design?
Like,
Well, design life, that is a big question, because we are trying to, work on this topic, because nowadays what we do, we start with an assumed design life, 50 years for each structure, and we have in our codes some prescriptions, I will say, okay, with this prescription, depending on the exposure conditions, you will have this service life guaranteed. But those prescriptions, which are basically maximum water cement ratio, minimum cement content, a UHPC automatically fulfills them. So this means that at least we have tried to, working out with, we built up this diagram here. Obviously, this one that you can see here is qualitative, but we worked to build similar diagrams for our structures. How do we build this curve? Well, you simply embed in your structural design equations a degradation model, for example, a chloride penetration or a sulfate erosion or a carbonation penetration. And as long as you have the progression of the aggressive front, either you remove it or you modify your equation consistently. Well, we ended up with numbers, and for this reason, immediately after that, I put higher material recycling, because you end up with service life of UHPC structures of more than 100 years, sometimes much longer than 100 years. But this has to comply with, real life, because we design a structure, but then there is an owner of the structure who may say, okay, but I need this structure for 30 years. And after that, I will decommit my site. So I am confidently enough with a shorter service life. So these materials we have been shown not only guarantee a longer service life, but if you think in a circular economy perspective, these materials also have a higher degree of recyclability, and you can repropose the durability performance. For example, Niranjan worked on UHPC made recycling UHPC. So we said the project is a zero waste project simply because we picked up the specimen, we crushed them, and we reused them. We did not dispose anything into the site. And the composition of this material, you have a lot of binder, you have low water cement ratio. In your mortar around the aggregate, there is a lot of material which is still potentially reactive. This is a way, to address the problem. It's not unique. Service life, if you compute it with any kind of available model, you have very, very long service life, which is the purpose of these materials, which may mean, for example, that in the span of service life, which is of interest for an owner, you may have very, very limited quasi-zero maintenance, for example, because your service life is surely much longer than that. You stay in this initiation time because you are able to extend this stage much longer than for ordinary concrete.
Thank you so much.
Okay, thank you.
So we have 15-minute break for the people who are attending online for the coffee break, and I think we will start at 11:35. Yeah.